Hello everyone, I'm very happy to be here tonight to talk to you about wave energy. So during this talk we'll address many aspects of wave electricity. So first, how are waves created and how do we generate electricity from them? And what could be the potential impacts of wave electricity on the network? So first, maybe a very short introduction about energy. We know that we need much more renewables in our electricity mix for many, many reasons. And the main one, you may know, you may be aware of all of them already. The first one is climate change. We have this big threat of climate change happening soon. We also see our oil and gas resources depleting, and that's a big problem regarding security of supply. And we have a rising concern about energy dependence to other countries. So regarding climate change, you're all aware of what that means or what that may imply in the future. But what's very interesting is that we can see here the visible effects of climate change here in Ireland, here now. I may name Professor Ray Bates from UCD, who's a renowned professor of meteorology and was doing one of the lecture series in 2010. He said that the terrible summers we've had in the past 3 years might be actually due to climate change. So that's a big incentive to fight climate change, I guess. Something we see as well is that the intensity of storms have been increasing in the past few decades. First, the frequency of storm events tend to increase. And when we look at the maximum wave heights that happen to occur during a storm event, it's increasing as well. So we might say we talk about wave energy, we talk about wave electricity, so that might be a great thing to have more storm events. But it's completely the opposite, because when we have a storm, we need to switch devices off to protect them. And when they're off, of course, they don't generate electricity. So in the end, that just decreases the amount of energy that we may get from the sea. So it's interesting to notice that climate change is not only strengthening the climate, but also our potential of renewables. Then looking at depletion of resources, we all know that oil and gas resources are finite and are just decreasing. That's a big threat to our security of supply. And a fact that's actually amplifying that is the growing consumption in emerging countries. So mechanically, it makes the prices increase, and that puts our society under a big pressure. Energy dependence. Something that might be a bit abstract, like this, but it's highly political. It's a highly political issue because energy is the backbone of our society. So if we put pressure or if we threat something about energy, then we're screwed in a sense. And that's absolutely true in Ireland because we import 90% of our electricity, of our energy from foreign countries. So if you look back at history, of course you may remember or know about the 1970s oil crisis. That had a big impact on the political energy strategy of Western countries. Something that's a bit more recent, I'd say. You may have heard that Iran decided to stop to sell oil and gas to Iran in the UK because they have a little disagreement about nuclear weapon, this kind of very not important thing at all. And another example, maybe if you're not directly involved in a conflict, you may be impacted by, as a collateral effect. If we look back at the gas crisis between Ukraine and Russia, there was a problem between Ukraine and Russia, but all of Europe was affected by this problem because 80% of the gas and oil sold by Russia to Europe is passing through Ukraine, so that's obvious. Then we had the Arab Spring last year. That was a sort of indirect effect as well. Of course, the Arab Spring is a very good thing, but as an indirect consequence, refineries were slowing down, and this had an impact as well. So even though it's not intended, energy could be a weapon. I mean, a threat on energy is a real weapon for a country. So it's important to get local resources like waves. Okay, So after this short introduction, I'd like to talk to the core about the core topic of this talk, which is wave electricity. But maybe getting back to the basics first, how waves are created. You know that the sun radiates over Earth, but not in an evenly manner. So you have places where they would get more solar power, and places where they would have less. As a result, there would be a temperature gradient, difference in temperature all across the globe. And you would have so cold masses of air, hot masses of air, and that would create winds. And these winds actually are created by convection cells and would create prevailing winds all around the world. Okay, so that reminds me that I should show you a very nice animation that's eventually working. Okay. Wind, when it happens to cross over the sea, would, by its friction with the sea surface, create waves. So that's a nice, gentle swell. But let's get a bit seasick, okay? That's obvious enough now. And this animation actually shows something that's very important. Waves are not a transport of matter. It's a propagation of energy. If you look at the boat, it's not, going from one side of the screen to another. It's just, going up and down, up and down. And that's what I would like to show with us, this big water particle here. They're not moving, they're just oscillating around a fixed position. Okay, so now we know that we have waves, and so how do we calculate the power from waves? Let's take a very school example of a nice, smooth sinusoidal wave. How we do to calculate the power of this wave is very simple. For 1 meter of wave front, of 1 meter width, we take the square of the height, multiply by the period. That's easy enough. It's a very theoretical example. But you're all aware that wave and the sea surface is very irregular. So how do we calculate power from this? What we do is that we have more or less the same formula, but instead of just the height of a wave and the period of a wave, we have statistical indexed, statistical parameters, which are HS and TE. HS is the significant wave height, and TE is the energy period. So it's not very important to know actually what they are. They're just statistical index, more or less, of wave characteristic. And from this formula, we can calculate the power of waves all around the world. And that's no surprise for you. Maybe you know that we have great resources, one of the best in the world, I'd say. And within Ireland, the west coast has absolutely huge resources. The east coast is a bit more sheltered, so there's a bit less of power there. But that might be interesting to look at that as well. Okay, let's be a bit greedy now. We may have a great benefit in integrating wave in our energy mix. First of all, I read a report done by the Ocean Energy Association of Europe, and they say that if we meet the target by 2020 in terms of ocean power and ocean generation, we might get, all around Europe, 26,000 jobs. I mean, by 2020, that's amazing, and when you know that in Ireland there's a great potential, you have reason to be optimistic. That could create, real good opportunity for coastal communities. That would really help the country. And another advantage as well is that besides jobs, we might get income from that. I mean, Europe needs renewables energy, renewable electricity. So what we could do is, just export the electricity we get here to Great Britain or to France. And that will be done thanks to this big, super grids you may see here, these big electrical networks. They're actually now, they're onshore, but some of them are being built offshore. So we already have the interconnection between Ireland and Great Britain. We have the interconnector being built between Ireland and Wales, I guess, yeah. And the one for France is planned for the next 5 or 10 years, I guess. So we're going there. Okay, so we have a nice plan. We want to transform wave into euros, but there's just something we've missed in the middle, and that's called a wave energy converter. So that's a device that would harness wave energy. So let's look at the the technical devices. There are many types of them. And the first one is called an oscillating water column. If you look at the animation here, you can see the sea level rising, and that would push the air up and down inside the enclosed air chamber here. And on the top of it, you may see a turbine, an air turbine. So having the air actually flowing here through the turbine would make it rotate, which would in the end create electricity. You have a practical example of a OWC device here. That's a device called the OE Boy from Ocean Energy, the Ocean Energy Company here in Cove. Another one is called a surge converter. It's quite different. It's basically a big flap, and you have a very practical example here with the oyster, very nice name for a flap, and it's just moving, back and forth with the waves. A very different one there. It's called overtopping. So you might see here, we have waves, and there is a big slope here, and the waves would ramp up that slope, look here, get trapped in a big reservoir, and then the water would be released to the ocean via a turbine here. So in principle, it's very similar to a hydraulic dam. An example you might see here is called the Wave Dragon, and that's a Danish company. Another one, the point absorber. That's basically a float, a buoy here, floating buoy, with a part of it which is submerged, and the relative motion between those two parts would create electricity. We have the Wave Bob company in Maynooth working on that principle. Another one, quite similar but still a bit different, is called the submerged point absorber. Still, we have this idea of relative motion between two parts of the device. But here, actually, the float, the submerged float, is pushed down when a wave is coming, because there is a huge volume of water just above it. So it pushes the floater down, and when the wave is gone, then it pushes the float is actually pushing up. So still this idea of oscillating movement. And we have the AWS company working on this very principle in the UK. The last one you may recognize because it's kind of very famous. It's called the Pelamis. It's named after a snake. It's a company in the UK working on this principle. It's called the device type is called attenuator. That's basically a hinge prototype bending like this. And we know that now how devices capture the movement from waves, and from Lenz's law, we know that if we have a magnetic field and if we have a conductor, if we have relative motion between the two created by waves, then we get electricity. So that's basically how it works. Okay. If you ask me at which stage the ocean industry is, I couldn't answer, because you may find devices at all the different stages that may exist at the moment. So I'll define a bit what these different stages are. The first thing, you have a great idea. You just put that on a draft, and then you say, okay, I may have to run some simulation to see if it's a real good idea. So you're at the concept design stage. So basically what you're doing is that you're creating a numerical model. You may run some simulation, hydrodynamics, and then you find that it's the best device in the world. It has an energy, maybe 90%. That's great. So you say, okay, let's go on. I'll try maybe to use a small-scale prototype, and I'll test it. So you build a scale prototype like this. The cup here, just here to show the size of it, if you will. So you put that in a tank, a wave tank, which is basically a big swimming pool. We'll see that later. Okay. So you undergo your test in the tank. You find it's marvelous. It's working extremely fine. So you decide to go to the sea. So obviously you need a much bigger device. The device itself might be quarter scale, let's say. Okay. So you undergo new tests. If everything goes to plan, you finally go to sea testing at full scale. That's, for instance, the oyster, the flap I've been showing you earlier in the slides, and it's being tested in EMEC in the UK. Okay, when I was talking about wave tank, I said it was a big pool, big swimming pool, and that's basically what it is. That's the wave tank of HMRC, the Hydraulics and Maritime Research Center for which I work. And I'll describe a bit what it is. Okay. So you've seen maybe this little yellow thing on the side here. They're here. They're the back of the wave tank. They are actually paddles. Each of these paddles can be independent, and they are actuated by servo motors, which means that each of these paddles can move in a very precise way, independently of the others. And with these paddles, we can create any wave climate we want. If we want to test a device which would undergo, I don't know, sea climates, like in the west coast of Portugal, you may do that. If you want to see what's like when the device is in the storm, you may do that as well. You know, just activating those paddles would create anything you want here. And the system is actually very sophisticated because it has even an anti-reflection system. Well, if you want the device to really feel like at sea, you should prevent waves to be reflected by the edges of the tank. So what we do, first thing is to have some material to absorb the waves, and they're basically, the material should be here. And another thing you might do is that the paddle should be intelligent enough to recognize a reflected wave, and instead of reflecting it back, it would just absorb it. So it's very impressive system, I'd say. Okay, so wave tank, that's an initial stage. Then you may go to sea testing. There are different test sites across Europe, but the most popular is EMEC, and then there is Galway Bay as well. And you may see here the OE buoy in tests, and that's the wave bob. And then the next stage is to go for commercial sites. So at the moment there is just one commercial site operating in the world, and it's a wave hub in the UK. It has opened maybe last year, I guess, yeah. But there are other test sites that are planned. Among the others, there are the Blavette wave test site in Ireland off the coast of Mayo. We have the BMEP test site in Spain. We have the SEMREV test site in France, and basically every country wants a test site because they want to make money out of it. So that's this picture you may see here is an artist's view of what the Blavette wave test site may look like. So first here you see the wave energy converters. There are just 4 of them, but they're just for making the sketch simple. There would be much more of them. Then those wave energy converters are connected to the shore via subsea cables. And then on the shore, you would find an onshore substation to step the voltage up so that the waveform could be connected to the national network. Okay, so that's great. That's a great idea. But before we can see actually those waveforms, connected to the network, there are still some aspects we need to investigate. And among those, how to design an optimal device. You know that at sea, you may encounter storms. So obviously, you want your device to survive. So in order to do that, you may need to build a strong enough device, which means putting more steel or putting more whatever you want to build your device with. But that has a cost. So how do we design a device so that it's strong enough to survive storms, but it's cheap enough to be competitive? So we have technically mechanical engineers working on that in HRC. Something else that's very interesting, that's a very nice picture, except that you don't have any wave energy converters in there, but you may pick up the idea anyway. That's a bit of the shore. So technically you can see here wind farms, you have offshore industry, you have onshore industry, you have ships passing here, you have fishing here, leisure activity, holiday makers, and finally you have animals. So basically the sea is a crowded place. So it's very important that we integrate the farm in a way that they'll be accepted by the population, the other users of the sea, and that all of that will happen harmoniously. So people working in law and social sciences are looking at it. How to make wave electricity be economically competitive? That's a big question, because while myself, I don't want to see my electricity bill rising again, so that might be interesting to have a cheap enough electricity. And the idea with the economics is to complement the technical. Well, when you need to make a decision, it's always important to have technical advice, but it's also good to have economical advice so that you're really getting to the optimal solution. How important are the local resources of a potential wave farm site? That's very important because we know more or less at a national level what the resources are. But if you're looking at different little bays here and there, you might not be sure of how much resources you may have. So it's very important to actually compute, to analyze that, because technically the amount of resources you may have actually means the amount of euros you can make out of the test site. So we have people working on resources assessment on a very detailed level. You may have observed as well that all of the wave devices I've shown earlier in the previous slides are oscillating devices. So as any oscillating system, they may achieve resonance. And resonance, that means that they may get, for a certain wave frequency, they may get a very high efficiency. So the idea is to, control the device a bit so that it would achieve a very high efficiency for different wave frequency. So that no matter what the wave frequency would be, it would always have a very good efficiency. So that's the work of control engineers. And the last one, which is basically the most interesting because that's what I'm working on, is what is the impact of a waveform on its local network. And I'll talk about the nice picture here in a few minutes. Okay, so we know now how to create electricity out of waves. What its impact might be on the grid. So first of all, a big recall. When we talk about grid or power system, they include overhead lines. I mean, that's obvious, but they also include power plants, transformers, and anything you may need to operate or to regulate the network. So in the old design of the old days, we had large power plants, and they were in a very limited number. I'm not quite sure. You may see the red dot here. That's the power station in Ireland. So they're very few. As a result of this design, we had power generated in a power station, and this power was transmitted to the customer via lines, and always in the same direction. So you go from power station to the customer. That's the old design. One additional characteristic of the current design of power system is that it's fully controllable. I mean, you have to predict the consumption of the population, and then you adapt the system accordingly. So, for instance, I guess there is a rugby match this weekend, so basically EirGrid would increase maybe the consumption for half time, because people would go to, maybe they would use the kettle or something. So they would technically predict the consumption on this aspect, sport events, political events, that kind of thing. So in a sense, I would say it's an easy management. We have a limited number of power plants. The power is always going from one direction to the other, and the system is fully controllable. No, that's where the fun begins. In the future, we hope to have solar power plants, wind, tidal, waveforms, etc. So those units, those power units, would be much smaller, but they would be in a larger number all across the country. And that would give some funny things, like a bidirectional power flow. instead of just getting from a power station to a customer, maybe now customer could become the power station and then give it back to the network. So it's, in a sense, it's kind of getting messy, I would say. If you have PV panels or small wind, you may become a power station on your own. In rural areas, if you have a farm, you want to put PV panels all around, well, all over the roof of the building of your farm, you're becoming an important power station. So an additional, well, difference with the old design of power system is a forecast error, because there we don't know when wind would happen. We may know that more or less, but there is still a little error. What you can see here is the air grid forecasts for last week. It was for 1 day last week. In blue, you may see the actual wind generation in megawatts, and in purple, you may see the forecasts. So there is a bit of a discrepancy here, although it's pretty close anyway. So in the end, the future the future method for operating the network would be a bit more complex. But I mean, said like so, it might be a bit frightening. But when we look at the very important share of wind energy at the moment in Ireland, we can really say that they're doing fine. I mean, it's complex, okay, but they're managing it, and the transition from the old design to the future design would be moderate enough for us to accommodate with that. So we might get on. Well, that's not only specific to wave, but that's common to all renewables. They would definitely force us to adopt new methods for operating the network. So now let's speak about the specific characteristic of wave power. I would like to establish a parallel with wind, because we might be a bit more familiar with wind. When we think about wind, we think that it might be constant over a couple of minutes, say, more or less. But the problem is that it's intermittent. So one day you may have wind, and 1 hour afterwards you don't have wind anymore, so that's a bit of a problem. As for waves, that's the opposite. It's not intermittent. It's always there. I mean, if you tell me that you can see a completely flat sea off the coast of Mayo, I wouldn't believe you. I mean, there is always wave out there. So it's not intermittent, but it's variable, and extremely variable. When we look at the graph here, you may see that you have a big peak, then it goes to zero. Peak, zero, peak, zero. So basically, the very problem of wave is this very big amplitude in terms of variation. That's the problem. And this power fluctuation caused by the wave form actually have a problem. They would induce voltage fluctuation on the network. And if we want to make it a bit more funnier, the network to which the waveform would be connected would add another problem to the existing problem. First, they're coastal networks, so they're peripheral networks, which means that they're much less meshed. That, in other words, they're much more vulnerable to any fluctuation happening on the network. If we look at those 2 points here, that's a point in Cork, so it's very close to Blavette, which is here, and that's a point in the center here. This point is connected by a much larger number of lines, you can see here, than this point here. So basically, this point is not as vulnerable as this one. We'll see what that would imply later in the slides. Besides, we had another problem, that the design is absolutely inadequate because it's reasonable enough. I mean, the power system there was designed for a rural population with a very scattered population. So it's not designed at all for exporting large amount of power. So based on those two ideas, that's why we call those networks weak networks. And a weak network actually means that for a given power fluctuation, the induced voltage fluctuation would have a much higher amplitude and would propagate much further in the network than if the grid was stronger. So we have a problem with waves that it's varying a lot, and besides that, the grid doesn't help us. It increases the problem. So that's basically my job, looking at the nature of the impact. So we know that we have voltage fluctuations, that we would have voltage fluctuations, but what does that mean? I mean, does that mean that we'll have overvoltage? Does that mean that we'll have disturbance? I mean, disturbance to the customers, or disturbance to the electrical network, electrical component connected to the network? Or does that mean that we will have unexpected disconnection of other power plants? We don't know yet. So that's what I'm investigating. And an additional aspect of that is to look at the geographical extent of the impact. I mean, would that be very local, or would that be much more widespread over a region? So one criterion we're looking at is voltage limits. Normally, voltage limits voltage must be maintained between fixed limits, which are actually defined by ESB or a grid. And if not, I mean, if the voltage goes out those limits, it might result in damage to the electrical equipment, possible disconnection of other equipment around. And if you disconnect one equipment without actually telling the grid operator, then other power plants might want to disconnect as well, and so on, and so on, and so on. So that would trigger, eventually, potentially, a chain reaction that would result in a blackout. So it's a very, very serious issue. Something else we're working on is called flicker, because voltage variation could actually cause variation in the light intensity of light bulbs, hence the word flicker. So that's a disturbance for the human perception. That's always annoying, but it might also affect the electrical equipment. And grid operators would set a very upper limit under which flicker level should always be maintained. Okay. There's been a huge work undertaken by the International Electrotechnical Commission to actually design a tool that would represent the flicker from a light bulb. And this tool is called a flicker meter. So technically, it takes a voltage time series as input and would output the flicker level. So how does that work? A flicker level, first stage, would take voltage time series like the one we can see here. So you have voltage here. That's, well, we call that per unit, but technically it's a percent. I mean, 1.05 per unit is 105%, and so on and so on. So we have block 1 taking this voltage time series as input. The second block would square the voltage that you'd have the light intensity variations. And that's a funny one. The block 3 and 4, they would actually reproduce the reaction of your eye and your brain to light variations. It's not how come. I mean, it's been tested over many groups of people to get the average reaction of an average person. So at the end of block 4, what you get is the instantaneous perception of light flicker. In other words, if you can actually see it or not, if you can see a light variation or not. And block 5 is actually performing a statistical analysis on your level of irritability. Because you may see a light variation once in a while, it wouldn't affect you that much. But if it repeats itself every 10 minutes, then you might be a bit annoyed by it, a bit disturbed. So block 5 is here to say, okay, it's happening too often, that's disturbing. Okay, so we have basically two criteria to look at power quality, to look at the impact of wave power on the network. That's voltage limits and that's flicker. You may have observed that I need voltage time series to calculate that. But how do we get from the power fluctuation in the waveform to the voltage, the power fluctuation on the waveform to the voltage fluctuation in the rest of the network? And that's where we need power system simulators. Power system simulator is simple. I mean, it just computes the voltage, the current, and the power at any point of the network. I'll show you how does that work. And basically, it could just simulate the power system behavior. For instance, what I could do is that I disconnect Cork and I see what effect it could have on Dublin. That's more or less the idea we do with power system simulator. We cannot touch the power system. It would be too much, well, harmful for us, harmful to the network, so we use this numerical tool instead. Okay. So power system simulator needs some data to compute a solution. So what I may say is that, okay, the waveform will output 5 megawatts, and I know that at this node in the network, we have 10.1 kilovolts for the voltage. So based on that, we'll launch the power system simulator, and it would find the unique solution based on the electrical engineering law that would actually be valid under the conditions I've put in the system. So as a result, it could say, okay, you have 5 megawatt here as input, but then due to cable losses and so on, you may just input 4.7 megawatts. And it will tell you also what's the voltage and what's the current at any point in the network. Well, both the network here, but also the network here, the national network. Okay, so we switch from the artist view to the real power system simulator. That's actually what I'm working on. That's the wave test site, the Blavette wave test site. You have here the waveform, then you have transformers offshore, you have subsea cables, then we go to the onshore substation, we go to the overhead line, and then that's the rest of the Irish network that's modeled here. So Blavette has been selected in 2009 to be the national wave test site of the Republic of Ireland, and we hope it to be completed by 2015, which is not sure because because of the economic crisis, it's been postponed. So I don't even know the date myself. Okay, and now that we have this network model, we need to represent the power fluctuation from wave energy devices. So I must say we've been very, very happy because we have experimental data, which is very rare in this field. We have data from this, the OE-Boy that I've been showing many, many times in the presentation here. It's based on the OWC device type. And this device has been deployed at sea between March and May last year. And that was part of a very big European project. And the OE-Boy has actually been selected for this European project with 13 partners from, I guess, 13 different countries, and for which HMRC was the coordinator. Okay, good. We have experimental data for one device that's a quarter scale prototype. So now we need to extrapolate that to create a full waveform, while including full-scale prototypes. So we do extrapolation on the data that we have to scale the power up. And another thing we have to do is to model the wave propagation, because as waves don't arrive at the same times at all the devices in a waveform, you need to represent this delay in the power output of the farm. Okay. Then you need to set simulation scenario up. The first thing we want to do, because the initial target for the waveform is 5 megawatts, we want to study that for 5 megawatts. But we know that this waveform would go maybe up to 20 megawatts if everything goes to plan. So we've performed the simulation for 5 to 20 megawatts. So megawatts is maybe a bit abstract sometimes, so let's put that in more practical numbers. 5 to 20 megawatts would mean powering 1,000 to 4,000 homes. Okay, so let's recall that now we have the network model, we have experimental data, we have extrapolated the data, we have the simulation scenarios. So we've done a lot of work already. Okay, so now you can say, I'm ready, let's go. First of all, before showing the result, which are the next slide, I'd like to make a very important point on what the simulation were. It's technically the nightmare of ESB. We wanted to know what was the impact of a waveform if we don't have any control systems, which are required though. I mean, ESB require every farm, power plants, to have control system. And we decided, no, we don't put in any control system for mitigating power fluctuation and voltage fluctuations. Technically, if this project was proposed to ESB, it would be refused purely and simply. So that's just simulation case, just to see what would be the worst case scenario. Okay, we have voltage limits. I told you about it. ESB says that the voltage, the maximum voltage, should always be below 1.1 per unit, which is technically 1/10% of the nominal value, the normal value. So we have two cases here, which is not very important in the end, but what you can see is that between 5 and 20 megawatts, it's fine. The voltage remains within the limits. And the same thing for the lower limit. The voltage in this case must always be above 0.9 per unit, which is 90% of the nominal value. So that's great. I mean, we didn't expect that. We expected voltage limits to be a concern, and that's not so. It's pretty fine. I told you about flicker level, and that's something we'll analyze. We have analyzed that as well. Flicker level technically should always be below 0.35, and we see that. For a power capacity of 5 to 10 megawatts, it's fine. But that might be a problem for 15 to 20 megawatts. But then I recall again, and I won't stop doing that, it was a worst case scenario, looking at in particular to the first stage, which is 5 megawatts. So of course, above 5 megawatts, there would be voltage control systems. And that would clearly decrease the flicker level that we have here. So those simulations are actually undergoing, so I cannot tell you what the results are. But at the moment, even a worst case scenario, even ESB's nightmare, it's fine. The waveform doesn't impact the network, and that's very good. Because I told you that we had a very weak network. In most places in Europe, they wouldn't have such a weak network. So they basically wouldn't worry about having a 20 megawatt waveform at all. Whereas we worried about a 5 megawatt farm. So we are very happy of the result in a very scientific manner. I'd like to conclude this study by EPP poor. It's great. Very happy of it. Okay. We had our moment of glory. So now we would like to move on and look at more different things. First, we will implement those control systems for voltage. It's very important for looking at different, for higher capacity than 5 megawatts. And there are other aspects that we need to look at, like the geometrical configuration of a waveform. Technically, if you put a waveform in a square shape, or if you put that in a rectangle or a circle, that may have different impacts on the grid. So we may need to find what's the configuration that puts the less constraint on the grid. Then there are many other issues that we may need to look at to really create a nice waveform. One of them is the design, including one or multiple cables. You may use just one cable to connect all of the devices, or you may use multiple cables. So it's a very interesting study, and it's still undergoing. So the idea of all of that is to find an optimal way to design and integrate a waveform to the network. Okay, if there is something to remember from this presentation, I hope that would be this, because you have a role to play in integrating renewables. We know we have a finite amount of resources, of renewable resources. But if we want really to live in a more sustainable society, we'll have to stop or slow down our energy consumption. And that would be actually possible. I mean, energy consumption doesn't only mean that you're, we can do the same, but with less. We may increase our energy efficiency. And we have to couple this renewable development with the energy efficiency. So for instance, you may yourself buy LED lamps, or you might be careful about switching light off when you're leaving the room, or you may even improve your home insulation. There are many different things that you may do yourself, and that will help to meet this target of living more in a more sustainable way. So we're coming to a conclusion now. During this talk, we've talked about the physics of sea waves. We've seen that we have large resources in Ireland. That's great. We need to harness that. We've seen what the benefits for Ireland could be in terms of jobs, in terms of income. We've seen what's the current development of the industry at this stage. We've looked at different potential issues for the integration of wave energy, and we've shown that initial studies say it's fine, but it needs to be continued. And other aspects, certain aspects, may need further study in the field of social sciences, in the field of economics. But fear not, you have a great team here with HMRC, very motivated people. Okay, so I thank you for your attention, and I would be happy to answer any question you may have.